Good evening, everyone. Good evening, everyone. In the last lecture, we discussed about the graphs of the different functions. Like we discussed the position time graph, we discussed about the velocity time graph, right? Where we conclude that the slope of a position time graph gives us the velocity, and slope of velocity time graph gives us the acceleration. And we also conclude that the area under the velocity time graph gives us the total displacement, right? And uh, And we could also see where the acceleration is positive, where the acceleration is negative, or where the motion is started one, or the motion is accelerated, right? So today we'll be starting with the acceleration time graph. We'll be starting with AT graph, that's the acceleration time graph. Let's suppose we have this Cartesian system here, right? This is our y-axis plane, and on the y-axis we're plotting. On the y-axis we have acceleration, and on the x-axis we have the time. That's the time axis, right? Let's suppose this is the acceleration time graph, right? If this is the acceleration time graph, it means it's a straight line parallel to the x-axis, or we can say that the slope of this graph is equal to 0. It means that acceleration is not changing. If the acceleration is not changing, so we can say that this is a graph of a constant acceleration, right? This is a graph of constant acceleration. So here the acceleration is constant, right? It's a graph of constant acceleration. Or we can say that velocity here, acceleration is positive, acceleration is constant. So if velocity here is increasing, right? Velocity is increasing. Velocity is increasing. So velocity here is increasing, acceleration is positive, acceleration is constant, right? We know that acceleration is nothing, it's a that's equal to dv upon dt, right? dv upon dt, or we can rewrite it as a dt will be equal to dv. If we integrate it on both sides, right? From both sides. So this will represent nothing. This will represent the area under acceleration time graph, right? Area under AT graph. So this represents the area under AT graph. So this is nothing. Let's suppose the initial speed is u and the final speed is v. So it will be the delta v, that's equal to v final, that's v minus u, or it's nothing. We call it as change in velocity, right? Change in velocity. So from here we can conclude that area under the acceleration time graph gives us the change in velocity, right? Area under the acceleration time graph gives us the change in velocity, right? So we can conclude here area under AT graph gives the change in velocity, right? So the area under the AT graph gives the change in velocity, right? So let's move on further. So area of acceleration time graph represents the change in velocity, right? It means that if this is the area, if this is the area under this graph, right? We calculate this area, right? This is the area under this curve. Let's suppose this time t equal to 0 up to time t. If we calculate the area of this curve, right? So this will give us the delta v, that's v final minus v initial, right? So that's nothing, that's the change in velocity, right? So let's conclude all these things, or we can rewrite, one more point is there, we can rewrite acceleration as v dv over dx, right? V dv over dx, right? So let's suppose if we have velocity versus position time, velocity versus position graph, right? It's the Vx graph, right? And let's suppose there is a velocity versus position graph. It's like this, right? This is the velocity versus position graph. So the slope of this velocity versus position graph is nothing that's equal to dv over dx, right? So it means that if we multiply velocity with the slope of Vx graph, that will also give us the acceleration, right? This will also give us the acceleration. This is also going to give us the acceleration. Or we can say that, suppose that if we take dx of the LHS, so it will be a dx, that will be equal to v dv. If we integrate it on both sides, it means this represents area under acceleration and position, right? Let's suppose this is the acceleration and position graph. This is the graph versus acceleration and position x. So let's suppose this is the graph versus acceleration and the position x. So the area under this graph is this area, right? This triangular part. So this is the area under this, right? So if we integrate it, it will be nothing. It will be v square minus u square upon 2, right? Here the limits are nothing. It's u to v. U is the initial velocity and v is the final velocity. And let's suppose this is initial acceleration a1 and the final acceleration is a2. So the area under acceleration position graph will give us nothing. Final velocity square minus initial velocity square upon 2, right? So this is one of the important conclusions here, right? With respect to the area under acceleration and position graph, right? So we're done with all the graphical analysis of motion along a straight line. We discussed position time graph, we discussed velocity time graph, right? And we discussed about the acceleration time graph, and we also discussed a bit about velocity versus position and acceleration versus position, right? So we'll be applying all these concepts to solve some of the problems related to the graphs, right? So let's begin with the problems. So here we have problem number 1. This is the first question here. The question is the displacement of a particle as a function of time is shown in the figure, right? The figure shows that. So here we have been given a displacement versus time graph, right? So we know that velocity is nothing, it's rate of change of displacement over time, right? This is also the velocity, right? Or we can say that the slope of displacement time graph will give us the velocity, right? This will give us the velocity. So it means that if we calculate the slope of this displacement time graph at any point, this will give us the velocity of the object at any point, right? So let's suppose that this is the point here. This is the point here. If we draw the slope at this point, this is the slope, right? This is the tangent and this will be the slope. At this point, this will be the slope. And at this point, this will be the slope, right? And here, finally, at this point, the tangent will be parallel to the x-axis, or the tangent will be the parallel to the time axis. We can say here the slope, or ds upon dt, is equal to 0, right? For a line which is parallel to the x-axis, the slope is equal to 0, right? So if the slope is 0, we can say that the velocity at this point is equal to 0, or we can say that at time t equal to 40 seconds, the particle stops its motion, or the particle comes at rest, or we can say the velocity becomes 0, right? So it means that here the slope was maximum, right? Slope was maximum. Or we can say the velocity was maximum at time t equal to 0, right? The velocity was maximum at time t equal to 0, and with time the speed of this particle, or the velocity of this particle, kept on decreasing and it became 0 at time t equal to 40 seconds, right? So we can say here, from this graph we can conclude that velocity decreases and becomes 0. Velocity decreases and becomes 0 at t equal to 40, right? So at time t equal to 40 seconds, the velocity of this particle becomes 0, because the slope here, slope of the position time graph or the displacement time graph here is equal to 0. If the velocity is decreasing, right? If the velocity is decreasing here, it means the acceleration here is retarding, right? It's a retardation, right? So we can say that acceleration is negative, right? Because the velocity here is continuously decreasing and it becomes 0 at time t equal to 40 seconds. So the two conclusions are there. Velocity is decreasing continuously and it becomes 0 at time t equal to 40 seconds and acceleration is negative here. So that's the conclusion. So let's move on to the question number 2, right? Let's move on to the question number 2. The question number 2 here is the graph between the displacement and time is given for a particle moving in a straight line is shown in the figure, and during the time interval during the interval OA, AB, BC, and CD, the acceleration of the particle is, right? We have to comment on the acceleration of the particle during different intervals, right? So you can see here the displacement time graph, it's a variable displacement time graph at this how the displacement time graph has been given, right? We have to see what happens to the acceleration at different time intervals, right? Let's suppose between OA, from between OA, we can see that between OA, we can see that here the slope of this curve is continuously decreasing, right? Slope is decreasing. Slope is decreasing, right? Slope is decreasing. You can see the slope is decreasing continuously. And at this point now, the slope becomes almost 0, right? The slope becomes 0, correct? So from O to A, slope is decreasing. It means the velocity is decreasing, right? Velocity is decreasing, right? And from A to B, slope is almost constant, right? We can say that A to B, if the slope is constant, right? Slope is constant, or we can say velocity is 0, right? If the velocity is 0, it means the particle is at rest between A to B. And from B to C, what is happening between B to C? We can see at B the slope is 0, but the slope is now increasing, right? Slope is now increasing. Slope is now increasing. Slope is continuously now increasing up to D, right? Slope is once again increasing. Or we can say that here in this case, from O to A, the velocity was decreasing. It means that we can conclude that acceleration, it's a retardation, right? It's a retardation. It's a retardation. And between A to B, the velocity is 0, right? Velocity is 0. It means the particle is at rest. Or we can say acceleration is also 0, right? Here acceleration is equal to 0, right? From B to C, the velocity is increasing. So velocity increases. Velocity increases. Or we can say acceleration is positive, right? Acceleration is positive, right? It's not a retardation, right? And from C to D, once again, velocity is increasing. Velocity is increasing. Or we can say acceleration is positive, right? Acceleration is positive here. Or we can say the acceleration here is in the direction, along the direction of velocity, right? So that was the conclusion from this displacement time graph, displacement position graph, not displacement position, displacement time graph, right? On the x-axis, it's a time, right? Let's move on to the next question. The question is that from the following displacement time graph, find out the velocity of a moving body, right? So this is the displacement time graph, or we can say that we can clearly see here on the y-axis, we have the time axis, on the x-axis, we have the displacement, right? So generally what do we do is that we plot, we keep displacement on the y-axis and the time on the x-axis, but here it's time on the y-axis and the displacement on the x-axis, right? And we know that velocity is nothing, it's the rate of change of the displacement with respect to time, right? Or we can say it's a slope, or it's nothing, it's the tangent, tan of theta of the point, tan of theta of the tangent, which makes with the positive x-axis at some point, right? So here we can find we can find the slope using this. That's the tan of theta. But we can see here, it's a time versus displacement axis, right? If it would have been the displacement is on the y-axis and the time is on the x-axis, then tan of theta would be here equal to velocity, right? Tan of theta will be here equal to velocity. But on the y-axis, we are having time. On the x-axis, we are having displacement. So the velocity will be nothing. Velocity will be equal to 1 upon tan of this 30 degree, right? It will be 1 upon tan of this 30 degree, correct? So the velocity will be 1 upon tan of this 30 degree, correct? So V is equal to 1 upon tan 30. Tan of 30 is nothing. It's 1 over root 3, right? Or velocity is equal to root 3 meter per second, right? So that's it. So we can calculate the velocity from the displacement time graph by using the tangent, right? Tan of theta, or the slope of the displacement and time axis, right? So root 3 meter per second is the correct answer for this question, right? So this is our question number 4, right? The question number 4 says that a particle is moving along x-axis, right? Particle is moving along x-axis. Its position is given by x is equal to minus 2t plus 3t square. So position versus time function is given as that is minus 2t plus 3t square, right? Minus 2t plus 3t square, right? And what we have been asked is that we have to plot the velocity versus time graph, and we have to plot the acceleration versus time graph also, right? Acceleration versus time graph and velocity versus time graph. So what we'll do is that we'll just calculate the velocity from here. Our velocity is nothing, that's equal to dx over dt, right? That's the first derivative of the position. So it's d over dt of minus 2t plus 3t square, right? So if we calculate this derivative, that is differentiation of t is 1, so we'll be left with minus 2, and differentiation of t square is 2t, so it will be 6t, right? So our velocity comes out to be 6t minus 2, right? 6t minus 2. What does it represent? It's a velocity versus time. If we see that it represents a straight line, right? It represents a straight line. If we compare it with the standard equation of a straight line, that's y is equal to mx plus c. So we can see c is the intercept here, c is equal to minus 2, and the slope here is equal to 6. And x is here t, and y here is b, right? So we have to plot this, right? So we'll plot it, velocity versus time. This is our velocity and this is our time, right? So intercept is the point where the line touches the y-axis, right? So at time t equal to 0, we get v equal to minus 2. That's our intercept, right? So at time t equal to 0, the velocity here is minus 2. Velocity here is minus 2. So if the velocity is minus 2, it will be on the negative x-axis, right? Negative y-axis. So this is the intercept, right? This is the intercept here, right? So minus 2 is our intercept here, and the slope here is positive, correct? Slope here is positive, right? So negative intercept with positive slope will be drawn like this. So this will be the graph of velocity versus time, right? So this is our velocity versus time graph. So this is our velocity versus time graph. We can see here the slope is constant, right? Slope is constant. If the slope is constant, it means that dv over dt is a constant, right? And dv over dt represents acceleration, or we can say that acceleration is a constant here, right? Acceleration here is a constant. We have to plot the acceleration versus time graph also, right? We have to plot acceleration versus time graph also. So we'll be plotting acceleration versus time graph here. So this is our acceleration versus time. We know the velocity is given as velocity comes out to be 6t minus 2, right? if we calculate the derivative dv over dt, that will be equal to 6, right? So dv over dt is 6. That's a positive acceleration, right? So it's a constant, right? So we can draw it like this. So it's a constant, 6. The value of this constant is 6. It means 6 meter per second square is the acceleration of this particle. So this is our acceleration time graph and this is our velocity time graph, right? So let's move on to the question number 5. The question number 5 says that a particle have initial velocity given as 10 meter per second. Its acceleration versus time graph is given, right? A particle having initial velocity as 10 meter per second and its acceleration time graph is given as find out its velocity at time t equal to 2 seconds, right? We have to find its velocity at time t equal to 2 seconds, right? So acceleration time graph here is a constant from O to, let me call this as P, right? We can call it this P, from O to P. It's a acceleration versus time graph, right? The acceleration is increasing, right? Here acceleration is positive. Acceleration is positive, right? And here also acceleration is a positive, right? Acceleration is positive but decreasing, right? But decreasing. The acceleration here is positive but decreasing. Here the acceleration is also positive but it's increasing, right? So from O to P, the acceleration is positive but increasing acceleration, and from P to Q, right? Let me denote it by point Q. From P to Q, the acceleration is decreasing but positive, right? So we have to calculate velocity at time t equal to 2 seconds, right? In the last class, we discussed that acceleration is nothing, it's equal to dv over dt, right? T over dt, or we can write this acceleration as a dt, that's equal to dv, right? From here, if we integrate it with respect to time, if we integrate acceleration with respect to time, right? And velocity with respect to velocity also, right? Let's suppose initially the velocity was u and final velocity is v. 80 area under 80, this represents the area under 80 graph, right? Area under 80 graph, right? This represents area under 80 graph, right? So it means that if we integrate this, this will be from u to v. So it is v minus u, that's delta v, that's the change in velocity. So this is our final velocity minus initial velocity, that is equal to area under 80 graph, right? Area under acceleration time graph. Initial velocity is given as at time t equal to 2 seconds. We have to find the velocity. A particle having initial velocity, that's initial velocity is given as 10 meter per second. So u is given as 10 meter per second. We have to calculate v, right? So we can write it here. So v minus 10, that's the area of this curve, right? We can see that this curve is nothing. This curve is nothing. It represents, this is the area. It represents the triangle, right? We have to calculate the area of this triangle, right? The area of this triangle is nothing. That's the half of base into altitude, right? Area of triangle OPQ, right? That's equal to half base into perpendicular. Base here is 2, right? And perpendicular here is from this point to this point. That's equal to 10, right? So this is the perpendicular here, right? So that's given as 10, right? So it means that's equal to 10, right? So final velocity will be nothing. V will come out to be 10 plus 10. That's equal to 20 meter per second, right? 20 meter per second. That's equal to 20 meter per second. So it means that the velocity at time t equal to v at time t equal to 2 seconds will be nothing. That will be equal to 20 meter per second, right? 20 meter per second. Suppose if the question asks us velocity at t equal to 1 second. If the question is like we have to find the velocity at time t equal to 1 second, right? Then what we will be doing is that we'll once again use the same concept, but now the area will be only because of this triangle, right? From this to this, because we have to calculate the area between 0 to 1 second, right? Because we have to find the velocity at time t equal to 1 second. So we'll be calculating only this area, right? This area. This area will be half base into altitude, right? So once again, it will be V minus U. That will be equal to area of triangle. Let me call this point as R, OPR, right? Area of triangle OPR. That will be half base. Base is 1 and the height is 10, right? So this will be equal to 5 meter. That will be equal to 5, right? So V minus U is equal to 5, or V is equal to 5 plus 10, that's equal to 15 meter per second, right? So the velocity at time t equal to 1 second is equal to nothing. That's at time t equal to 1 second, that's equal to 15 meter per second, right? So at time t equal to 1 second, the velocity is nothing. It's equal to 15 meter per second, correct? So the velocity at time t equal to 1 second is equal to 15 meter per second. Let's move on to the question, next question, right? Let's move on to the next question. The question is, velocity time graph for a particle moving in a straight line is given by this graph. Calculate the displacement of the particle and distance traveled in first 2 seconds. We have to calculate the displacement of this particle and the distance covered by this particle in 2 seconds, right? It's a velocity time graph. We can see it's a straight line graph, or we can say the slope here is negative, right? We can see that acceleration here is, the acceleration is negative, or we can say it's a retardation, right? It's a retardation here, right? Because the velocity here is positive, but the acceleration is negative. It means that both velocity and acceleration are in opposite direction. It means the speed of this particle is decreasing, and we can see that at time t equal to 0, at time t equal to 1 second, the velocity becomes 0, right? The particle comes at rest. And we know that area under area under AT graph, or area under VT graph gives us the displacement, right? It gives us the displacement, right? If we have to calculate the displacement of particle, we have to just calculate the area under this VT graph, right? So this is the area under this VT graph, right? Let me call this as A1 and let me call this as A2, right? And we can see that this area is positive here, right? And this area is negative here, right? The upper area is positive and the lower area is negative. So we'll calculate both the areas. So displacement S will be equal to area of this triangle, right? So it will be half of base into altitude, that's 1 into 6, plus, or we can use minus half of base into altitude. Base is 2 minus 1, that's 1, into height, that's once again equal to 6, right? So it means that's equal to 0, right? So the displacement here is equal to 0, right? It means displacement 0 here means particle moves here like this and comes back and reaches the same initial point, right? Reaches the same initial point. So here in this case, displacement will be equal to 0, right? Displacement is equal to 0, right? Now from the same graph, if we have to calculate the distance traveled, right? From the same graph, if we have to calculate the distance traveled, right? If we have to calculate the distance traveled, so distance traveled will be nothing. Distance will be equal to, we will just, we will not take the negative area here. We'll take this area also positive, right? We'll take this area also positive. We'll not take it at negative. If we take this area as positive, then the total area will be calculated as the distance traveled, right? So we'll take this area as well positive, right? We'll not take this area as negative. We'll get the total distance, right? So the total distance will be half of base into altitude, that's 1 into 6, plus half of base into altitude, that's 1 into 6, right? So it will be 2 times upon 2 into 1 into 6, that's equal to 6 meter, right? So it means the total distance here is equal to 6 meter, or we can say that from this point to this point, the distance is 3 meters, and from this point to this point back, the distance is once again 3 meters. That's why the total distance is equal to 6 meters. So here the displacement is 0, but the distance traveled by this particle is 6 meters, right? So this is our next question. The question is that we have been given an acceleration versus time graph, right? Here's the acceleration versus time graph. This is how the acceleration versus time graph varies, right? Initially, what happens from time t equal to 0 to time t equal to 2 seconds, the acceleration is increasing, and then acceleration is constant, and then acceleration is decreasing, right? Continuously up to time t equal to 8 seconds, right? The question is asking that we have to calculate the velocity at time t equal to 2 seconds if at time t equal to 0 velocity is given as 5 meter per second. It means that initial velocity at time t equal to 0, the initial velocity is given to be as 5 meter per second, right? It's given in this question. So initial velocity is given as 5 meter per second at time t equal to 0. We have to calculate the velocity at time t equal to 2 seconds. And once again, we can use the same concept that area under the acceleration time graph gives us the change in velocity, that's delta v, or that's nothing, that's v minus u. But here from t equal to 0 to t equal to 2 seconds, the area will be this one, right? This is the area. This is the area between time t equal to 0 to time t equal to 2 seconds, right? This is the area we have to calculate. So this area will be calculating between time t equal to 0 to time t equal to 2 seconds. So this area will be nothing, that will be equal to half base into altitude, half base is 2, and the height is 10, right? So it is 10, right? Initial velocity is given as u, that's given as 5, right? That will be equal to 10, and the v will be equal to 10 plus 5, that's equal to 15 meter per second, right? That's equal to 15 meter per second, correct? And we also have to calculate the maximum velocity from time t equal to 0 to time t equal to 8 seconds, right? It means we have to calculate the maximum velocity as well. See, look at this graph. The acceleration is continuously increasing and it is positive. It means that it's along the direction of the velocity, right? So acceleration increases continuously, and then at time t equal to 2 seconds, the acceleration becomes 0, or we can say the acceleration, we can say the velocity becomes constant, right? Here the slope is 0. Here the acceleration becomes constant, not constants. Acceleration versus time graph, it's given as acceleration versus time graph. Here the acceleration is constant, right? Acceleration here is constant. We have to calculate the maximum velocity, right? Maximum velocity. It means that here the velocity is continuously increasing between time t equal to 0 second and time t equal to 4 second. Velocity is increasing, right? Velocity is increasing, right? Velocity is increasing continuously. Between time t equal to 0 seconds and time t equal to 4 seconds, velocity is increasing continuously. Here the acceleration is constant, right? Acceleration here is constant, right? So if the velocity is increasing, so it means during time interval 0 to 4 seconds, the velocity is continuously increasing, and then acceleration here is negative, right? Acceleration is decreasing, right? Acceleration is decreasing, right? Acceleration here is decreasing. Acceleration here is decreasing, but positive, right? But positive, correct? So from 4 to 6 seconds, between 4 to 6 seconds, between time t equal to 4 seconds and time t equal to 6 seconds, acceleration is once again a positive, right? Acceleration is once again a positive, but the acceleration is decreasing. It means that if acceleration is decreasing, but it is still positive, it means the velocity is still increasing, right? So velocity is still increasing, right? Velocity is increasing, right? Velocity is still increasing. So velocity is still increasing. It means that from 0 to 6 seconds, from 0 to 6 seconds, the velocity is continuously increasing. And from 6 to 8 seconds, the acceleration now becomes negative. If the acceleration becomes negative, it means now the velocity is decreasing, right? So it means the velocity actually increases from 0 to 6 seconds continuously. It means that at time t equal to 6 seconds, the velocity will be maximum, right? And at time t equal to 6 seconds, the velocity will be maximum, right? Velocity will be maximum, right? So at time t equal to 6 seconds, velocity will be maximum, right? So it means we will calculate the velocity at time after time t equal to 6 seconds. We'll get to know about the maximum velocity, right? So once again, we'll use the same concept that our change in velocity will be equal to v minus u. That's equal to area under AT graph, right? Area under AT graph, right? So between 0 to 6 seconds, this is the area, right? This is the area. So it makes a trapezium, right? It's a trapezium. It's a trapezium between 0 to 6 seconds. And we know the area of trapezium is nothing. It's half of sum of parallel sides. Sum of parallel sides into distance between them, right? Distance between them. We can see in this trapezium between 0 to 6 seconds, the parallel sides are this side and this side. These are the parallel sides. The length of this side is 6 and the length of this side is equal to 2, right? So the sum of parallel sides is 6 plus 2, that's equal to 8, and the distance between these parallel sides is equal to 10, right? We'll just write it. That's 6 plus 8. The distance between them is 10. So it will be equal to 6 plus 8 is 14, right? 14 over 2 multiplied by 10. That's equal to 70, right? 70. Or V will be equal to 70 plus initial velocity was given as 5 meter per second. So it will be 70 plus 5. So it means the maximum velocity of this particle will be nothing. It will be 75 meter per second, right? So this is the maximum velocity. So this is nothing. This is the maximum velocity. So this is the maximum velocity, right? So let's move on to this last question here. The velocity versus time plot of a moving object is shown in the figure, right? The average velocity of the object during the first 10 seconds is. So average velocity is nothing. P average is defined as, it's a total displacement over the total time, right? Over the total time. So total displacement over total time. And we know the total displacement is nothing. It's the area under the velocity time graph, right? It's the area under the velocity time graph. And this area is positive here. And this area here is negative, right? So this is a positive area, this is a negative area. We'll be just adding these two areas to calculate the total displacement. So total displacement here will be, this is a triangle here, so it will be half of base into altitude. Base is given as from here to here, that's 5. And altitude is 5 once again, that will be multiplied by 5, right? And then minus half of base, that's 5. Once again, from here to here, that's 5. And height is once again equal to 5, right? We can see that the total displacement is 0 upon the total time. That's, let's suppose delta t, that's equal to 10 seconds, right? So if the total displacement is 0, it means that average velocity has to be equal to 0, right? So the average velocity here between 0 to 10 seconds is 0. So V average is nothing, that's equal to 0, right? Because the total displacement is equal to 0. And in this question, if we have to calculate the average speed, right? Average speed. So average speed will be nothing. It will be total distance plus the total time, total distance upon the total time. So the total distance will be this area plus this area. We'll not be taking this area negative here. We'll be taking this as a positive area to calculate the total distance. So it will be half of 5 into 5 plus half of 5 into 5, right? Upon the total time. That's 10 seconds, right? So it means that average speed will be here equal to, that's 25 over 10, that's equal to 2.5 meter per second, right? So this is the average speed, right? and average velocity is nothing, that's equal to 0, right? The average speed here is 2.5 meter per second and the average velocity is equal to 0, right? So that's it for today, and we're done with the motion along a straight line. In the next lecture, that will be on Monday, right? The next lecture will be on Monday. So we'll be discussing there on Monday the projectile motion or the motion in a 2 dimensions, right? Till then, take care and goodbye.